Hello, we are back discussing Euler's method, which is an approximation technique to find or approximate values for the solution to initial value problems where we're given the derivative is equal to an expression in f of x comma y, and you're given an initial value y of x sub 0 equal to y of 0, and we identify a particular step size that behind the scenes defines the density pretty much of the slope field that was used to derive Euler's method. And we know that x sub n will always be an incremental increase in that step size. So x sub 2 would be equal to x sub 1 plus h. And h is defined as the step size. And our approximation for being able to approximate the output to the solution to the differential equation without actually solving the differential equation is y sub n equal to y sub n minus 1 plus h, which is your step size, times the derivative evaluated at the previous point. So here is an example. Use Euler's method with step size 0.2 to estimate y of 1, where y of x is the solution of the initial value problem y prime equal to x squared times y minus 1/2 y squared. And our initial value is y of 0 is equal to 1. So that means x sub 0 is 0 and y sub 0 is 1. And we know that the output of our solution set is, is y of 0 equal to 1. So first you want to build a table, and if you have to do really small step sizes or you have to do many iterations of Euler's method to get to a particular output you want, you might want to consider using something like Excel to make automatic calculations, because what you're going to find is that it's a bit tedious. So some people do use bigger step sizes but their estimate is not going to be as accurate. So here we go. I built a table of y sub n's and x sub n's. And so first off, in the first column of x sub n, we know that x sub 0 is equal to 0. And note that x sub 1 is just going to increase by the step size. So we go from 0 to 0.2, and then x sub 2 increases by another step size, 0.4, and then we increase by another 0.2, 0.6, another 0.2, we get to 0.8, and then finally we get to 1. And remember, we're trying to estimate the output y of 1. And so we want to understand that once we do get to x sub n equal to 1, where we do after the fifth step, we know that y sub 5 is going to be evaluated at x sub 5, and that is going to give us our y of 1. So whatever answer we get for y sub 5 is going to be our approximation. Good. So let's start. I also went over to y sub n, and I'm using the Euler's method formula, which came from tangent lines from our slope field. And y sub 1 is going to be, just using that formula up above in Euler's method, y sub 1 is supposed to be y of 0 plus h times the derivative evaluated at x sub 0, y sub 0. Y sub 2 is going to be y sub 1 plus h times the derivative evaluated at x1, y1. And y sub 3 is y2 plus h times f x2, y2. And y sub 4, and so on. So now let's actually start making those calculations, and we are going to have to use the x squared y minus 1/2 y squared. So we can start off with the very first one, and that's going to equal, we know what y sub 0 is. Y sub 0 is 1. We know what h is. H is 0.2, and we know that x0 is 0, and y sub 0 is 1. So I'm going to be calculating that value. So this is going to equal 1 plus 0.2, and now I'm going to be using the formula in there for our slope. So this is going to be 0 squared times y, which is 1, minus 1/2 times y squared, and y squared was 1 squared. And I get that this is going to be equal to 1 plus 0.2 times minus 1/2. And what value do I get there? I get 0.9. Good. So I'm going to take that 0.9 because that is going to be my y1. And for that 0.9, I'm going to want to put that in here, and I'm going to want to put that in there. So if I continue going in the very next step, this one, my y1 is going to be 0.9. My h is still going to be 0.2. And now I'm going to be calculating. We know what x1 is. x1 is going to be, our x1 is 0.2. And now we have our y1, and our y1 was 0.9. And now I'm going to begin again. I'm just going to make that calculation. I'm going to use 0.9 plus 0.2, and I'm going back, and now instead of using zeros and ones, I'm still using that x squared y, right? This is our derivative. That is our f of xy, is this value here, and that's what I'm doing in there. So, and using the calculations of 0.2, so now I've got 0.2 squared times y, and y is 0.9, and then I have minus 1/2 0.9 squared, and I end up with 0.8262. Good. And what do I do with the 0.8262? I am going to take that value, that is my new y2, and I'm going to want to put that, and let's change this color. So I will make that blue, and that's going to go here, and it's also going to go here. Good. And we know that x2 is going to be 0.4, and where does that come from? This is our x2, and we want to put that in there, right? So I'm going to begin again, and we get that this is going to equal, our y2 is 0.8262 plus 0.2 times f of 0.4, right? Because we're going up the previous value, 0.4 times, or comma, 0.8262. And that's going to equal 0.8262 plus 0.2 times, and we're going 0.4 squared times 0.8262 minus 1/2 times 0.8262 squared. And what value do I get there? Do I have enough space? Maybe I will. And what value I do end up with, so this value here is going to be 0.784377756. I don't know if I'd want to use that unless I had the Excel. But I'm going to be using that value, right? And that value is my y3, so I'm going to, I'm going to put that in here, and I'm going to put that in there. So here I go again, and I might just skip ahead to the other one. We do know that this is going to be, and I'm just going to shorten it and say that that's 0.784. I'll just use that one. And then I'm going to go plus 0.2, and it is going to be times the f of 0.6 now, because it's going to be x3, and x3 is 0.6. So we have 0.6, and we're still using 0.784. And so that's going to be 0.784 plus 0.2 times 0.6 squared times 0.784 minus 1/2 times 0.784 squared. And what value do we get here? We get, I'm getting 0.77932. And that is my new y of 4. So if I begin again and go to my y sub 5, if I use this dark blue, that is my y sub 4. And so I would be using the y sub 4 in here and the y sub 4 in there. So writing out my numbers again, in y sub 4, I get 0.779, and that's what I'll shorten it to, just for clarity, plus, the more accurate you are, the more accurate your estimate will be. F of 0.8, because we do go up one step size, we're using x sub 4, and remember x sub 4 is 0.8, and we're going to use 0.779, and that's going to be 0.779 plus 0.2 times 0.8 squared times 0.779, take away 1/2 of 0.779 squared, and I end up with 0.8183468676 if you used all of the numbers. And what is this? This value is y sub 5, and remember our input was 1, and so now I can say that y of 1 is approximately equal to y sub 5, which is 0.8183468676. So notice I did not solve the differential equation, but I was able to come up with an approximation of an output for at x equal to 1. I didn't go through a slope field to find the shape of the graph. I can go through that and find and put in my initial value and get an overview of the general shape of the solution estimate. Or I can use Euler's method to find just a particular output, and that can be useful in various applications. Like if I have a marginal cost function and I want to output a cost of 500 units, but I have the marginal cost function, but I can't, and that's the derivative of the cost function, but I can't solve the differential equation, I can estimate the cost of output for 500 units by using Euler's method. Okay. So it's pretty simple, but pretty tedious, and I do recommend using Excel or some other automatic calculation to generate the table, but you get the idea, hopefully. Thank you. And next up will be linear differential equation.